Nice. Thank you for coming today. Today, my topics is imaging techniques and 3D imaging. So first, sorry. Okay. First, I'd like to introduce myself briefly. I'm Manako Yamaguchi, MD, PhD. So I'm an obstetrician and gynecologist. So I came from Niigata, Japan. So I have worked at Gomez and Sequeira Lopez Lab as postdoctoral fellow since January 2023. So my hometown, Niigata, is famous as best rice production place of Japan and also known to great seafood. So therefore, Niigata is a wonderful place for sushi in the world. So today's topics. First, I'd like to introduce the type of the microscope very briefly. So for students. So then I focus on the tissue pH and 3D imaging technique. This slide shows the resolution of the microscope and our eye. There are two fundamental types of microscope, light microscope and electron microscope. Electron microscope differ from light microscope in that they produce an image of the specimen by using beam of electron rather than the beam of light. The electron has much shorter wavelength than visible light, and this allows electron microscope to produce higher resolution images than standard light microscope. Light microscope let us distinguish objects as small as bacterium. The most powerful electron microscope allows us to distinguish individual atoms. And for light microscope, there are two main tissue embedding methods: paraffin embedded tissue and fresh or fixed frozen tissue. So as a paraffin embedded tissue takes time and effort to create raw, but much better morphologic detail is obtained and better visualization for HE and structural cell analysis. And they can be stored for long time at room temperature. So on the other hand, the fresh or fixed frozen tissue is easier to prepare than paraffin. In particular, fresh frozen tissue can be sectioned immediately after embedding, and therefore they are used in clinical work for rapid intraoperative diagnosis. And frozen tissue is good for immunofluorescent images, and staining protocol are shorter than paraffin. But morphologic detail is not usually well preserved than paraffin, and they have to be kept at low temperature. So ample storage space needed. Okay, so this is two major types of light microscope: bright field microscope and fluorescent microscope. Bright field microscope is simplest and most common technique used for illumination of sample in light microscope. For bright field, staining is often required to increase contrast. Here I show the typical staining method for kidney pathology. Hematoxylin and eosin stain is one of the principal tissue stain used in histology. It is the most widely used stain in medical diagnosis and is often the gold standard. In HE staining, the cell nucleus is stained purplish blue, and extra matrix and cytoplasm are stained pink. Fast staining is mainly used for staining the structures containing a high proportion of carbohydrate macromolecules like glycogen, glycoprotein, and proteoglycans. In the kidney, fast staining mainly demonstrates the basement membrane, mesangium, and the tubular basement membrane. The Masson polychrome stain is common connective tissue staining. Mucous, collagen fibers, and reticular fibers are stained blue or green, and muscle and nuclei are stained red. And of course, we usually use bright field microscope for immunohistochemistry. IHC is a technique to image antigen in tissue using antibodies binding specifically to antigen. Okay, so next, also we frequently use fluorescence microscope for immunofluorescent staining. The fluorescence is a physical property of the object that absorb light in one wavelength and emit the light of the different wavelengths. Usually, wavelengths emitted by fluorescent substance in higher wavelengths than the light is absorbed, which simply means that absorb blue light and emit green light. So visible light is usually in 400 to 700 nanometer range, and wavelengths commonly used for cell biology observation is usually in 300 to 800 nanometer range. In fluorescent microscopy, there are two ways to visualize target protein. One is a genetically bind fluorescent proteins like GFP, YFP, or TD tomato to target protein. And other is used a fluorescence labeled antibody or dyes that bind specifically to the target protein. Okay, so by combination dyes or the proteins, the GFP or YFP of different wavelengths, multi-proteins can be observed in the same section, like this. So this is a nuclei, and this is a smooth muscle, this is a renin, and this is a nerve. So, this is one of the strengths of the fluorescent staining. Okay, here I show the various types of fluorescence microscope. A wide field microscopy is most common type of fluorescent microscope. In this microscope, illumination and detection of the fluorescence are done through the same light path. And the next one is confocal microscope. It pinpoints the focus of the laser beam to the desired position in the sample, thus obtaining the sharp image without unnecessary illumination. So this type of fluorescent microscope allows high-resolution 3D imaging of thick sample to be analyzed without physical sectioning. However, imaging techniques such as confocal microscopy that image points require a huge amount of time to acquire high-resolution image of larger sample. So hence, light sheet microscopy that can image plane instead of points, thus improving the speed of imaging dramatically. So using laser light sheet microscopy, large samples can be imaged at subcellular resolution if the tissue is made transparent. Therefore, the next topic is tissue clearing and 3D imaging. Recently, the development of techniques that combine tissue clearing reagent and advanced imaging techniques has made it possible to observe whole tissue without slicing. But before we talk about this technique, first of all, why should we need to observe tissue in 3D? So it's not 3D enough. So the example listed here are 3D case for observation in 3D. First, for convoluted 3D structures, 2D cross-sectional view can be misleading. For example, tubular structures are fragmented in 2D, so making it difficult to see continuity. The second, if cells have complex distribution, 2D cross-sectional view may not accurately quantify complex spatial relationship. Finally, for rare cell and microstructures, 2D section might not provide enough sampling to identify and quantify such type. Here, I'd like to present an example of real-world application of 3D imaging. This is my past study in my PhD degree. Here is this is 2D histology of human uterine endometrium. The endometrium is inner lining of the uterine lumen. The composed endometrial glands and stromal tissues. So as you know, the human endometrium undergoes cyclic regeneration and shedding every month through menstruation. The stratum basalis is the layer that remains intact during menstruation, and stratum functionalis is the layer that is replaced with each menstrual cycle. So traditionally, the similar schema has been used in human endometrial histology for many years in textbook and reviews. As you can see, the bottom of endometrial glands depict as blind end. So, but I doubt that was correct 3D structure. So therefore, to determine the 3D morphology of normal human endometrial glands, I used tissue clearing and 3D imaging. I cleared human endometrium tissue and stained them with fluorescent conjugated anti-CK7 antibody to label endometrial glands yellow. So then imaged cleared tissue with light sheet of fluorescent microscopy and reconstructed them in 3D using imaging software. So thus, I succeeded in visualizing the detailed 3D structure of endometrial glands. As shown in this movie, one of the strengths of 3D imaging is ability to enable the observation of continuous tomographic images of tissue in all directions. I observed the 3D image of endometrium very carefully. As a result, I discovered a new characteristic morphological feature of human endometrial glands. As you can see, some glands connect at the bottom of endometrium. This connection was not sufficiently visualized by previous 2D histology. So on basis of this 3D observation, we provide a new concept of human endometrium histology. In the stratum basalis, so the endometrial glands are not blind. They form the plexus network and expand horizontally along the muscular vein. So we named this plexus network rhizome. So this term rhizome comes from rhizomatous plants such grasses. The name was chosen because basal plexus and rhizome are not only morphologically similar but also functionally similar, that they can prevent erosion. Thus, the 3D imaging has the potential to elucidate the essential structure of tissue that have been overlooked in the past. So here, I'd like to explain the procedure in detail once again about the tissue clearing and 3D imaging. Now we can choose various tissue clearing reagents and protocol for tissue clearing. Images taken using microscope capable of taking Z-axis stacked image, such as light sheet microscope. In this method, tissue is required to be fluorescently labeled in some way. Z-axis stacked images are reconstructed in 3D using imaging software. The key concept behind tissue clearing technology is reducing heterogeneity of the refractive index in sample. So refractive index indicates the light bending ability of that object. So for example, when the glass rods, they have a refractive index 1.517. The mass in the liquid of same refractive index, the glass appears to disappear because no light is reflected. However, the complex composition of biological sample produce a heterogeneous refractive index. So this heterogeneity scatters light. The clearing can be achieved by removing water and lipid and fulfilling the space with RI matching reagent. Thus, as a tissue clearing technique aimed to establish a straight line path through the tissues. This allows the fluorescent laser to illuminate deep into the tissue. Okay, so in recent years, various technique clearing reagent and protocol has been developed. Most clearing protocol can be divided into the following modules: fixation, liquidation, and optional steps: the calcification, bleaching, staining, and optical clearing. Optimization of each process is necessary to better sample preparation. The liquidation is most crucial part of the protocol because it directly influences transparency. Strong liquidation are necessary to achieve high transparency, but the liquidation has a negative impact on antigenicity and brightness of the fluorescent signal like YFP and GFP. And organic solvent-based imaging solutions are often difficult to prevention of protein fluorescence like GFP and YFP. Instead, aqueous-based methods such as cubic, I usually use it, are well suited to imaging fluorescent protein. However, even with cubic, detection of fluorescent protein decreases with longer liquidation period. So therefore, the liquidation must be optimized to achieve good transparency while preserving the signal. For 3D imaging, the source of fluorescent signal must be decided. If you have fluorescent reporter transgenic mice, so you can use endogenous fluorescent such as GFP, YFP, or TDTON. On the other cases, the additional staining will be required. The fluorescent conjugated primary antibodies or combination primary and fluorescent secondary antibodies or nuclear staining is usually used to give anatomical orientation. And finally, optical transparency is obtained by immersing in a solution that homogenizes the refractive index. So this is a mouse kidney. So you can see that by homogenizing the refractive index of the tissue and immersed in the mounting solution with the same refractive index, the tissue has become completely transparent. So now, I'm currently working on the application of 3D imaging to kidney vasculature and Rennie cells. So because Rennie cells are unique characteristic and of changing distribution within the renal artery tree in development and in response to physiological stress. I think Rennie cells and renal artery tree fulfill all the conditions suitable for 3D imaging. So voltage structure, complex distribution, and rare cells. So it is difficult to accurately understand these three-dimensional structures and their distribution from 2D cross-sectional sections alone. So I'd like to show this is a normal kidney 3D imaging. So this mouse is Lehmann-Shikri MTMG mouse. So the Lehmann-Shikri lineage cells labeled green. There another background structure labeled red, and I also added alpha smooth muscle staining. The structure of the vascular tree, the distribution of Rennie cells, and their position in the relation to the glomerulus can be understood very clearly. In contrast, during development, it is reported that Rennie expressing cells cover most of the trajectory of the blood vessels. As the maturation is completed, Rennie expressing cells become restricted to the juxtaglomerular area. So I tried to verify the distribution of Rennie cells in this development stage in the 3D as well. So this is the P0. P0 is a newborn mouse kidney 3D imaging. This time, this mouse is Lehmann CTD tomato mouse, Rennie expressing cells labeled red. And I also added smooth muscle cell staining and labeled green. So you can see in the vasculature tree of the developing kidney, venous cells are widespread in the larger vessels, and almost entire length of the afferent arteries is covered by venous cells. So thus, you can see the detail of the distribution of the venous cells in 3D. So finally, our previous studies have shown that long-term RAS inhibition leads to concentric hypertrophy of renal arteries. But this arterial phenotype was revealed by 2D observation of renin and vascular staining of the kidney sections. So it is difficult to accurately understand the 3D structure of more complex blood vessel only 2D sections. So this is the 3D image of renin knockout mouse kidney. They show the concentric hypertrophy. So this mouse renin neural cells labeled green. And also I added the smooth muscle cell immunostaining. So you can see the vascular tree is thickened throughout, and the renin neural cells are distributed to further surrounding the vascular muscle cells, forming concentric vascular hypertrophy. Accumulation of renin neural cells is more pronounced near glomerular inflow area like this. So the like forming goblet-like shape that covers the glomerulus. And this is a serial cross-section movie of the renin knockout mouse. So you can observe morphology of the concentric hypertrophy at one cell resolution. Oh, sorry. Okay, so you can see small smooth muscle cells accumulate concentrically at afferent arteriole and interlobar artery. Renin neural cells further surrounded the smooth muscle, covering the afferent arteriole. Oh, sorry. And the accumulating encircles the glomerulus. Okay, so finally, I'd like to show the future perspective of 3D imaging. The 3D imaging is expected to be combined with omics analysis as well as analyzing tissue structure. Here is the concept of spatial omics. The omics analysis by single cell sequencing provides huge amount molecular expression information, but cell location information is lost. On the other hand, 3D imaging allows comprehensive collection of spatial location information. The spatial transcriptome analysis, such as Visium, geomics, feature have been popular in recent years, and Cosmics and Xenium is the latest high-plex in situ analysis platform performed on 2D sections. And this year, Visium HD, a spatial transcript analysis with single cell resolution, finally become available. So the current tissue clearing technology is not suitable for the reading RNA information. So therefore, it is difficult to connect the cleared tissue to high-plex in situ hybridization or sequence technology directly. However, I believe that deeper understanding of the true distribution of cells and their positional relationship of surrounding structures through 3D imaging will enhance the quality and understanding of these spatial omics analysis based on 2D sections. In addition, just recently, the techniques for reconstructing the 2D high-resolution spatial transcript analysis in 3D was published by PCEN. So perhaps within next decade, the spatial omics analysis in 3D will become commonplace. So that's all. Thank you so much.
We have that technical.
Oh,
Yeah, both of them.
Yeah, thank you. That is my son. Thank you so much.
Any questions? So I have a question.
Mhm.
So you said the mounting solution?
Yes.
The clearing,
Yes.
it needs to match the refractive index, right?
Mhm.
How do you do that? How do you, it's,
Mhm.
how do you make the you measure the refractive index?
Yeah. This is a set that we can buy.
Oh,
Yeah, already as a yeah. The company already
okay.
made it. Yes, the mounting solution. I bought both. The just RI adjusted reagent and the mounting solution. I bought both of them. Yes. So, this is in this case, cubic required to the RI adjustment reagent and mounting solution. But as some case, another protocol, the only the RI adjustment reagent, the directly use
Gotcha.
for the
Okay.
mounting solution. In this case, we need to buy.
Buy
both.
and you can shop for a different refractive index mounting solution. For example, if the refractive index is different.
Yes. If the RI adjustment reagent refractive index is different,
Yeah.
you need to choose the matched
No.
reagent. Yes.
Is the index dependent on the tissue clearing method or the tissue?
Method.
The method.
No. Yes. The every tissues using this protocol can get
Okay.
this.
152.
Yes. This is depend on the reagent of the clearing protocol. Yeah.
Yeah, this one, another question I have,
Yes.
for when you use the antibody for 3D imaging,
Mhm.
you always prefer the primary antibody conjugated with the fluorescent labeling, right?
I usually use it. Yeah.
Instead of going primary, secondary.
Yeah, but this way also available. The many people use the second about the primary antibody and fluorescently labeled secondary antibody.
It works also.
But
Okay.
also, the unspecific reaction the increase. Yes, therefore and more longer time to need to stay pure. So therefore I like the labeled
Mhm.
primary antibody only. Yeah.
Any other questions?
I have one question about the 3D image so this is on the tissues, but is there any even higher resolutions on the single cell level to visualize the specific molecules distribution in a single cell?
The single cell and more high resolution, right?
Yeah, for this 3D imaging. Microscope.
I think, but the one cell, single cell and inside the cell, right?
Inside or on the cell surface, whatever.
Yeah. I think it is suitable to the confocal microscope, not light microscope is a little bit more large.
Yeah.
The confocal is more clear. It's the single cell level. Yeah. It is as you can choose the purpose. Yeah.
I have a question. What's the software you used to make the video?
Okay. Yeah. Yes. I use the Imaris software.
Image.
Imaris. Not image. Imaris software. yeah,
Imaris.
Imaris, yeah.
And
Alright.
Yeah. Sorry. So Imaris. Imaris.
Imaris.
Yes, Imaris. We can look at the advanced microscopy facility.
Yeah.
Yeah, they open, so we can look. Yeah, we can use.
And we can take the so many sliders together, but I don't know how to make the video. Thank you, thank you so much.
Yeah. Okay. Thank you.
You can stop the recording.
Okay.